is Larisse Voufo of the University of Indiana at Bloomington, right?
Yes.
And she will be speaking on quantum circuits.
Alright, so I guess he already did the introduction for me, so, well, more particularly I'm going to be talking about translating circuits from the standard network model to the one-way one. And actually, I'm here presenting this work that with my advisors, I'm a subject general office from Indiana University. I myself am visiting Einstein Foundation for a year. So, why would we care about such a thing? Well, as interest and needs for experiments in the one-way model increase, of course, the needs to translate those circuits that already exist in various other models, especially the ones from the standard circuit, into the one-way one increase equivalently. So what we're looking for here is for the translation to be systematic and straightforward. We want it to be efficient, meaning how fast is the algorithm running, as well as effective, which means, well, how helpful is the final realization based on, with respect to our particular realization needs, whether they're physical or implementation related. So, and the same idea can apply to many other models, as we will see. So our main goal here is going to be to set counts for work towards a complete translation calculus, satisfying, of course, the conditions that I just showed earlier. In our paper, we gather a number of tools to work towards such a translation from current works, analyze their respective limitations, and extend them into some more user-friendly ones. And in the process, one of our hopes is to also provide an alternative information for understanding one of those complex one-way realizations that we find in common papers for nowadays, at least for me most often. So naturally, the translation can follow various different paths based on the structure of the circuit. And it turns out that one of the most important part of the scheme will be the composition of one-way realizations or one-way circuits. And then some optimizations if needed. So now, one of the most generalized and systematic ways to compose those circuits in the one-way model nowadays is defined as a measurement calculus, which relies on applying a number of standardization passes, which are symmetric transformations on the composition of two patterns that describe the circuits that we want to compose. So for example here, after extracting the command sequences, right there, the command sequence out of the pattern that define these two circuits, 1 and 2, intuitively, the first thing we want to do is propagate the entanglement commands from the second circuit across the correction and measurement commands of the first circuit, and then do the same with the measurement commands from the second circuit across the corrections. The point being to get the composition, the final pattern, get this command sequence in a standardized form where entanglement comes first, followed by the measurement, followed by the correction. And somewhere in here, there is something that we refer to as introduction of shift commands on each measurement, and then propagating those shift commands across the remaining measurement commands and corrections. So anyways, this whole process, as I just described, constitutes part of the translation algorithm that we refer to as concatenation and standardization algorithm. And the very basic first one that we define is actually, has a little bit more than naive efficiency in this sense that it runs some of the passes implicitly. So, now it seems like at this point we should be happy with what we have. But what is the problem? Well, as the circuit size increase, the patterns so defined become more and more complex and less user-friendly, I guess. And meanwhile, the CNS algorithm becomes more inefficient. As a solution in our paper, in the first time, there is a number of helper inequalities that we can use implicitly to improve the CNS algorithm. But more importantly, we define a more abstract way, we propose a more abstract way to define patterns, which pays attention to answer the qubits only as necessary while maintaining a direct relationship with the circuit model. In the process, we also describe a more visual way to concatenate the circuits, and as well as, this visual way is based on the graphical representations of the circuits that we want to combine. as well, and of course there is also an more approximation-based version of it. Both of those graphical concatenation bring us to some interesting version of the CMS algorithm. So, this is the abstraction I'm talking about. Now, let's see how straightforward it is from the circuit model. Basically, one can view this as having a number of inputs that we apply on some functions representing each gate here and getting these outputs. In standard quantum mechanics, of course, the return operation here can be viewed as the vector, and this bind operation is called bind, is a matrix vector multiplication. Now, these two, the bind and the return operation, are actually monadic operations that hide all the quantum magic, and I'll explain myself pretty soon. Those familiar can actually see that this work stems from work that was done by Bisotto and Armasabri, and I think it was Alton Kirch, and in the work, they related unusual features of quantum computation with the semantic constructs of monads and arrows from the theory of programming languages. So it turns out that circuits in the circuit model and the one-way model and any other model can be represented using this exact same notation. Now, as an example of how complex the circuits can actually get, and to talk more about the quantum magic that is hidden, this is what the pattern definition for the circuit we had before would have looked like. And then this, after some standardization, with these parameters, of course I'll let you be the judge of how complex it is compared to the abstract representation. Now, let's replace the monadic operations in such a way that the underlying monad is actually the graphical representations, and voila. So, here, these are some, these arrows represent which logical output becomes logical inputs. And we go through a number of transformations and we finally get this as the final circuit. Now, how does this make sense, and why these transformations are valid? We look at those qubits, those logical output qubits that become logical inputs in the process, during the process of composition, and we notice these interesting conditions. Actually, we look at the correction operations, the correction commands on the logical output, and the measurement commands on the logical input, with respect to the final measurement in the final circuit. And it turns out that the measurement is only affected when the correction is in X and the measurement is neither in X nor Y, in which case the measurement becomes dependent on the C signal. There are some shifts. In other cases the measurement is unchanged, but there are some shifts that we introduced here and there. And in addition, when the correction is in X, the shifts are introduced on the neighbors of the qubit as well. So, of course, this gives us a newer version of the algorithm, which is actually even more efficient in the sense that there is a sizable improvement in the programmation time. But the only potential the only potential source of inefficiencies happens to be platform implementation dependent, and here I'm thinking about the particular programming language in use during the simulation. So this is actually a reliable basis for designing more efficient versions that this time will be particularly specific to the implementation platform we're using. So as far as the approximation goes, in our paper we restrict ourselves to whether measurements are adaptive or not, and to the particular measurements of x, y, and plus or minus pi over 4. And of course one can verify that in this case, those, what I call interleaving qubits, with adaptive measurements need no further analysis, as we can probably read. And anyway, so we took that restriction and plug it into the alternative CNS algorithm and get this very simplified version of it, which only consists of asking ourselves whether this condition is met, and then blindly translating the conversions of the circuits, blindly converting the representation of those logical inputs into the ancillary representation, while conserving the measurement. And this is all we actually had to do for the graph representation that I showed earlier. After this one. That's all we have to do to do these transformations. So now we're done with concatenation optimization. Well, what we did is we gathered a number of those commonly known optimizations that are actually abstractly defined in Wessendorf's paper. And we basically gave an automated reinterpretation of those optimizations in terms of the standardization passes that are used by for the measurement calculus. And we define these additional optimization on the other side. Of course, these can be viewed as a generalization of the converse, can be generalized as converses of these ones. And the classification has to do with the realization mates. Now, done with the optimizations, now let's look at some practical example. And we took a look at this addition circuit from Kokau et al., which is supposed to be more efficient than commonly known quantum addition circuits, in the sense that it reduces the number of ancillary U's down to a single one from a linear bound. And in addition, the authors also defined this sort of version, which is supposed to have a higher parallelism by lowering the depth and number of gates. Following our translation scheme, we come down to these two realizations. And, well, I don't think you guys can see that very clearly, but somewhere here we use the introduction of Z measurement as a feature to maintain the grid representation, and the propagation of identities here to connect the outputs and the inputs accordingly in order to extend the 1-qubit addition sub-circuits into the 6-qubit one. And there's an interesting result. It doesn't matter whether we're using whether we start the transition from the optimized or the non-optimized version of the addition circuit. And the reason is because those optimizations were only modifying those gates that were in the Clifford group, which can only affect the spatial and operational resources. If we really want to make a change in the temporal resources of the depth, we want to be modifying those non-Clifford operations accordingly. So I think I'm pretty much done here. At this point we're hoping that we've set enough grounds for the work towards the complete transition calculus, and that we've definitely given an additional information for understanding those complex realizations. And something to point out though is it's going to be, one will find it quite imperative to explicitly express measurements that are outside of the XY plane in this complete translation. And of course this runs our experimental range a little bit, and way for flexible navigations. Flexible navigation experimentations with different types of graph states. And of course this can be extended into any other type of models, and not just be limited to the standard model and the one-way one. And as usual, there is always a number of interesting questions that our paper discusses as well, and I'm inviting the interested to take a look at it. Thank you.
Are there any questions?
I don't know much about it, find this very interesting. Just to give you an idea, you have this 6 quantum bit gate for addition, and then you produce this one-way circuit. How big is this entangled state you start from, the one-way circuit then? How many qubits would you have to entangle?
How many qubits would I have to entangle?
Or how many qubits are involved in that state? Is this a translation of your 6-qubit?
Oh, the circuit, you were talking about the circuit that I translated?
Yes.
It was a 6-qubit addition circuit.
Yeah.
And how big, like...
I mean, how many qubits will be involved in this cluster state you start from in your one-way computation?
Well, I think, I mean, it depends on whatever universal set you start from. So when you start the translation, and, well, let's go back to the circuit I had previously. Okay, here, so when you start here, you have all these different gates that you want to find some one-way realizations for. And when we come to the graphical representation, here, this is the representation of the control phase. This is the control knot, control phase, and all those things. And, well, of course, we connect the input and outputs as with respect to what is in the circuit model, and start applying the transformation, the symmetric transformations that in following the scheme that I define in the next slide. And so how big and how many qubits depends on actually whatever set of universals your realization you start from. Does that answer it?
Any other questions?
Well, maybe a comment. Like last week at the main conference, Ros Duncan and I presented a paper, because you mentioned this question about doing measurements outside of the XY plane, and we have some sort of graphical calculus. I don't know how it's connected to this, in which we actually have these measurements outside of the XY plane as part of a graphical calculus. And it sort of subsumes the measurement calculus rises, and so I would assume that there's some kind of connection of these representations with those more topological things.
Yeah, that is actually interesting, because it's not that it's impossible to measure outside of the XY plane according to the scheme, because there is definitely, I mean, you can just apply rotations or anything like that to do that. But it turns, at least I found that it makes sense to just be able to say measure in Z rather than giving another rather than writing it any other way, including the other ways. Well, I mean, that's what I did with the introduction of Z measurements and optimizations. Anyway.
Okay. Any more questions? So then we move on to the next speaker, who's Ellie Dillon.